Okay, we're back to the next video. So in the last video, I talked to you about the different types of orbitals and the shapes of those orbitals, where each orbital would start, at which level, and understanding how many subshells exist for each, or how many orbitals exist for each subshell. So the next step, and this is where we're ultimately headed to, is to be able to um, draw out or predict the where each of these electrons in each element will exist. So there are rules that have been developed for how each electron in an individual element will fill these orbitals. So I will say this is where we're going to start in our lecture this week. So we will go over all of this again, but I want to make sure that you have this option to review this video um, for additional information if you get confused from this. This is actually one of the more challenging parts for some people, is how to do this. So the previous information I talked about was really background leading up to this section, which is the how to use it and what we really need to know moving forward. Okay, let's just start with a couple rules. So they each have names, and they were obviously developed by a series of smart scientists, etc. The first rule is the Aufbau principle. One is, and that states that electrons will always occupy the lowest energy orbital first, so they will fill in order. You would then fill an apartment building from the lowest floor. If you're building a hotel, you would then choose your cheapest room first. It's not a particularly easy, but the idea is as the energy increases, it takes a certain amount of energy to fill each particular level. It's further out from the nucleus, and therefore, um, you will be filling them in order. However, what gets complicated is some orbitals actually overlap, and we're going to need to know what that looks like. This is another diagram that we would use to show how you would fill these. And again, this is one of those things where you're just going to have to memorize these orders. They're fairly straightforward. There are some pneumatics and pictures we can use to teach you. But basically, if you look at this, you would start with 1s, then you would jump up to the next level, which would be 2s. But then you notice that, and then you would jump to 2p. So this follows what's logically. S is a simpler orbital, p is a little higher energy orbital. You go 1s, 2s, 2p, and that fills you. Each one can hold 2 electrons, right? And so that's what you said. Then you move up to 3s. That follows fairly straightforward. Then you go to 3p. But what happens here is that 4s is actually at a lower energy than 3d. So if you follow this, and we will go through this again, you'll see that the order of the filling of each orbital will be 1s, 2s, 2p, 3s, 3p, 4s, 4d. So what you'll see is that the d orbital will actually fill after the next level of S. So here's another diagram. This is actually usually the most helpful way I think people find to figure this out. You could draw this star step method and go through this. And I will go through this in class and show you how to do that. But this might be one of those things you just put on your notes, is that you write down what the filling order would be as described here, and you just follow it as we start building these configurations. So ultimately, what I'm going to be asking you to do is to show me a configuration, which I will then describe to you in a moment, as to where all the electrons in an individual element exist. Okay, moving to the next section, we are getting to the idea of what I'm actually going to ask you to do, which I'm going to ask you to build an electron configuration. If you go back to the previous slides where we talked about the how many electrons can go in each orbital, you will then be expected to figure out how to load them. There's a particular format for an electron configuration which uses the shell subshell for notation, which would be like 1s or 2s, right? And then for each of those subshells, you would then use a subscript. A superscript to indicate how many electrons you would have in each of those orbitals. So for example, just a brief example is to assume the electron configuration of oxygen. We know a neutral oxygen has 8 protons and therefore 8 electrons. So you have 8 electrons that need to be filled. You would start with 1s orbital, which holds 2. You would then go to the 2s, which is the next energy level. That holds 2. And then the next energy level from that would be the 2p. But 2p can fill at 6, but you only have 4 left. So you would put those 4 in there. We'll break this into a lot more detail or later, but this is really how you would build electron configuration. So the electron configuration of oxygen would read as 1s2, 2s2, and 2p4. We will go through many examples of this, so don't worry if this doesn't make sense yet, but I just wanted to introduce you to this concept. Okay, so how would we do this? Going back through again, we're going to write an electron configuration. We're going to find out the number of electrons in each of the atom we're interested in. So in the case of oxygen, we figured out Z equals 8, it's neutral, and there's 8 electrons. Remember, if it was an ion, you'd have to adjust that. But because the number of protons and electrons are the same, because it is neutral, you would have 8 electrons. Then you will be filling your orbitals and your subshells from the lowest energy to the highest. We know the order is 1s, 2s, 2p, 3s, 3p, 4s, etc. We know that each orbital can hold a maximum of 2 electrons and that p subshells have 3 orbitals, right? So I'm using these terms confusing. But within the p, you have 3 of these orbitals, and therefore the total across p would be 6. And I will draw this for you in class if this is confusing. It's hard to do this in this format, but how you're going to be filling them is the 1s fills with 2, which would have 6 left over. The 2s fills with 2, you have 4 left over. Then you go to 2p. You know it can hold 6, but you only have 4 left, so you would then put those remaining 4 into that configuration. This is what we're going to spend a lot of class time doing and practice, but just introducing you to this concept. Um, for some examples of how these might go, hydrogen has 1 electron, that would be a 1s1. Helium has 2 electrons. We would fill that full 1s subshell to 1s2. Lithium has 3. You would fill the 1s subshell and jump up to 1 electron going into the 2s, etc. Ultimately, you will find that when you get down to the noble gases, you will fill the entire p orbital. This will explain as we move forward into why neon is so stable. It has a full subshell. Um, the entire level 2 is full. Both the s and the p orbitals are full, and it really likes to be there. That is the most stable state. So leading forward and we talk about reactivity, you will see that this is the essence of understanding the reactivity of the individual elements. Has to do with whether you can get a full shell. And that is the most stable configuration. Okay, moving to that, we then bump into the next level of rules. So the next thing is the Pauli exclusion principle. Each orbital, or therefore subshell, an orbital within a subshell can hold a maximum of 2 electrons. So I'm using these terms interchangeably, and I'm going to try to clarify for you. An orbital is the specific orbital that holds the 2 electrons. The subshell is the one that these orbitals exist in. And I know that the language can be very confusing, and they are often used interchangeably. So I'm going to try to make this clear. But within each orbital that can hold a maximum of 2 electrons, those 2 electrons must have opposite spin. One will spin up and one will spin down to avoid repulsion in sharing that space. Now, how you define the spin is outside the scope of this class. So just remember that that means indicating an arrow up or an arrow down. And I'm not going to get into the specifics of what that means, other than to say when you draw these pictures, you will be required to draw one up and one down to indicate that they are going in opposite directions and therefore do not repel each other the best to minimize this repulsion. Okay. The other one is that when filling orbitals of the same energy, for example, the 3p or the subshells in a 3p, so px, py, and pz, electrons will occupy each orbital singly. So you'll go 1 in px, 1 in py, 1 in pz before you start doubling up. This is the analogy. Well, the analogy I like to give sometimes is the idea of getting on a bus. If you got into a bus and there were 2 seats per row, and you saw somebody seated that you don't know, a stranger in a seat, you're not going to intentionally sit next to them on purpose. You're going to find an empty row first. You're not going to fill the seats next to a stranger until there are no available empty spaces um, left. And so you're going to always fill the empty row first. And once every row has one person in it or one electron, that's when you'll go back and start filling the next rows. Okay, so those 2 rules will help us to then go to the next thing we're going to learn how to do, which is a orbital diagram. So unlike an electron configuration, which is just letters and numbers, an orbital diagram is a picture. It's a box that indicates how these individual subshells and orbitals are filling, where you would then indicate the spin on the electrons. So if you look at the very bottom of the page, the difference between electron configuration and orbital diagram. Electron configuration would say 1s2, where an orbital diagram shows a box with the 1s under it, indicating the two electrons, one pointing up and one pointing down. So in this case, you're using the Pauli exclusion principle to indicate that one has to spin up, one has to spin down. And you would also be using the Hund's rule as we get to more complicated, where you would have to indicate using this which one you're filling first. So in an electron configuration, you're never going to be indicating which is the spin of the electron, nor do we worry about breaking the p, d, and f orbitals into their individual, or p, d, and f subshells into their individual orbitals. But you will be doing that in orbital diagrams. So that's why most people find orbital diagrams to be much more complicated and difficult than the electron configuration. So we'll do some practice on that in class. Okay, just to show you some examples of how this works. You would then, it's often easier to start with the electron configuration and then build the orbital diagram from that. The first picture at the top does show you how you would build the helium one, where we draw a box for each orbital. You would then put the two electrons in it. If you go to lithium, where you would show you have 1s2, 2s1, the 1s box has two electrons in it. The 2s has only one. As we're building into more complicated, you would then build these in a little bit different way. So let's just looking back at the oxygen example. You would then, we had said the 1s orbital was full. So you would make a box with a 1 up and a 1 and down. Sorry that these are not boxes. It's hard to do this in hard to do this in Google Slides, but we'll do this in class. The 2s then fills the next box, which would be labeled 2s. I don't have the labels on here. Using Pauli exclusion principle, you would have a 1 up and a 1 down, and then you have 4 electrons left. First, you would fill each of the 3 boxes, 1, 2, 3, with the spin up, and then come down and fill the remaining 1 with the spin down. Okay, so that's how that would look. Looking at some examples, and these make it much easier to see. These would be examples of how you would convert an electron configuration to an orbital diagram. So for nitrogen, for example, we have a full 1s orbital. Those have the spin up and down. Electrons indicated. The electron configuration shows 1s2. The orbital diagram shows a box with 1s and 2 electrons in it, spinned it with spin up and spin down. You then have the 2s2. That's indicated by a box with labeled 2s with a electron pointing up and pointing down. Then you have 2p3. So the important thing to note in this is you've broken the 2p into the 3 individual boxes. P's will always have 3 boxes, D's will always have 5. Sorry. And then F's would have 7, which although we don't do very many of those. Important to note that the spin up, each of the electrons is in a separate box spinning up. As you move down 1 to oxygen, that box then fills first one. Fluorine, the next one, would then fill the second one, and it's not till you get to neon that you have all 3 boxes filled with an up and a down. Now you see in this demonstration, they show an arrow with just a single loop. That works fine. You can also do full arrows. It doesn't matter. This is just something that is done often for pictures. Either way, a full arrow up and down works as well, and that this is just a shorthand for how to draw it more in a more simple way. Okay, so that is let's just